Okay, hello. I wanted to make a shorter video as kind of a follow-up to my last Transformer video. This is sort of an add-on to that project. Basically, what is happening in this file is we are using a similar model structure, so the Transformer model structure, or at least part of it, applied to the task of image classification. So to get started, I'll explain what I mean by image classification. This is the dataset that I'm working with, the CFAR 10 dataset. If you want to get more details, you can look this up. The long and short of it is that we have these 32 by 32 images that fit into one of 10 classes. Yeah, that's pretty much all we have to say about it. RGB images 32 by 32. So going back here, I guess I can, I did like minimal data processing for this project, or at least for this part of the project. I think that the data came in this format. I don't think I did anything here except maybe this. But basically it comes split into 5 pieces of uniform volume. So I just made 4 of them the training data, and one chose one as the eval data. So that's what I'm using here. When we have our train function, we are sort of going through for every epoch, we are going through 1 to 5. That's how we access the file. And for the eval, we're simply kind of using the same code, but hard coding that fifth that fifth file. Okay, so I'll start with the machine learning portion of this project. Here I have 2 new classes for this file. And so these were sort of custom written for this application. However, I am reusing the transformer encoder block. So everything under here, including the multi-head attention and the dot product attention functions, all of that is the same as we would have seen in the machine translation portion of this project. The reason that I could not reuse the classes as they were, so I believe that for the encoder, that forces the embeddings on at this point. We're doing the embeddings differently. For the encoder, there would be this sort of embedding layer here, and that would be added that would be added to the inputs at some point. We're not doing that here. We are actually using, first off, a different style of embeddings. We still care about positional embeddings. I guess before I should talk about that, I should talk about how we are processing the data sort of at runtime. So the data is coming in through here, and we have these 2 unfold functions. This is sort of a similar process to convolutional steps. So we have unfolding, basically taking, we have this patch size function here for the width and the step. One of these functions is going to be going across the row dimension, and one of them is going to be going across the column dimension. And the effect at the end of the day is similar to convolutional steps. We are going to wind up with, instead of a series of word embeddings like we did in the machine translation portion of this project, we're going to wind up with a series of image data embeddings, so to speak. It actually is the raw image data, but then once we run that through linear layer, it sort of becomes very analogous to a set of word embeddings. So that's what's happening here. I will do a step through so we can take a look at the data as we go through to sort of get a handle on what exactly that looks like. Okay, so something that I forgot to mention there is this positional embedding. We're treating that a little differently than we did in the machine translation part of this project. Basically in that project, we were more or less, I would say, hard coding the positional embeddings. So we had that sine and that cosine function generating sort of unique vectors and applying those on the words, and the model can use that to identify order. Here we're actually taking a looser approach where we are generating these random embeddings and having that be a learnable parameter. So basically we are putting, well, this gives us more learnable parameters. I think that this is useful in applications where the order might be more loose and we are letting the model learn about which order. We are letting the model learn which relations in order are the most important. So just for example here, we have patches that are taking these convolutional steps over a 2D image, but I guess you can imagine that the patches, it might be more important for them to interact with the patches adjacent to them. This is something, I mean, that technically could happen, I think, in the machine translation application, but here it lets the model kind of learn that and have that knowledge exist on the embedding layer as well. So that's what's happening here. With that, I think that we can begin a sort of step through with debugging this. So I'm going with the non-class token mode here. And we are going to end up. So first off, this is going to, this is before these sort of like convolutional steps have taken place here. So looking at our input X, right, so we have a batch size of 128, 3 channels of 32 pixels by 32 pixels. So just to demonstrate what this kind of looks like, if I do this, so it has taken, it has performed this sort of unfolding process along so the second dimension here, and you can see that the second dimension, it's been divided by 4 from 32 to 8, and then we have this 4 happening on the back. Then this process is going to happen once again. And so now we have our steps over both the rows and the columns. In this one, I'm doing a permutation. So if we look at x.shape, patches.shape. So we have our channels and then our 2 sort of patch. This is going to be like an array of patches, an 8x8 array of patches. I'm moving the channels to the end to just so it's adjacent to the pixel values. If we look again, so 128 batch, 8x8 array of patches that are 4x4, each of those having 3 channels is what we end up with. Then we are going to sort of squish that last part together. And we wind up with, we're going to squish the 8s together as well as this section on the end. And we wind up, so 128, a sequence of 64 patches, each of those containing 48 pixel values. So now we can start, we can generate these sort of patch embeddings. I have this lazy linear here, which is just setting it to essentially a hidden dimension, to use the terminology from the machine learning translation part of the project, and also positional embedding. These are the 64 positional embedding values that are getting imposed on that sequence of patches. It is not class token mode, so let's ignore that for now. The transformer, so I'm not sure if I'm even going to step in here. Oh, sorry, so this is the transformer because it's really just passing it through the blocks. I'm using this none for the valid lens here because all of our patches are going to be considered in each instance of the batch. So I'm just this means that no masking takes place, and all of the values consider each of the other values when that attention function is being performed. So going through here, and then we have our classification. So looking at our X now, we have our 128 batch length by 64 patches by 128 of just kind of context. We are going to perform this mean function here, and to look at x.shape once again, now we just have our right. So 128 batch length and 128 context vector or 128 context vectors of length 128 through the multi-layer perceptron head, and we have our prediction. This is a pretty standard loss function here. I will run through once again using the class token approach, and then we'll just compare those two approaches. Okay, so I've set the class token mode to true, and we'll go through that forward function again, looking at how this path is a little different. Basically, we're going through the same process here, where these patches are being generated here, applying the same embedding, so going to embeddings and applying our learned positional embeddings. And then we have this class token mode here. So this class token, which is created up here, yet another learnable parameter. So that is, just to look at it, sorry, self.class. So we have, for each batch, we have one vector of length 128. We are going to be concatenating that with our x. So our x is those 128 batches of 64 length of patches. Basically, all this to say at the end here, we have that 65th element in there. That's going to go through the transformer. And at the end, we are only considering, so in this case, we'll have the same output shape, but here we are slicing across the batch and across the hidden dimensions, but only ever examining the first token in that sequence of, so it's our class token and then 64 patch tokens. Basically, our class token is carrying all of the context here. So if we look here at X, now we just have those for our batch length, our 128 context vectors of length 128, similarly to how we got that in the mean mode, but generated in a different way. So the last thing that I want to show is sort of the results. So I ran each of those modes for 10 epochs using TensorBoard. So we'll take a look at the TensorBoard graph output. So here we have, I just took one eval measurement at the end for each, and then for the train values, I was taking the accuracy and the loss. To give a very quick summary here, basically the non-class token method, which I called mean, outperformed in this application. That sort of makes intuitive sense to me, in that you're simply taking you're taking a wider range of input information. If you're doing these calculations across all those class tokens, why would you just look at one class token? But supposedly there are instances where the class token does make sense, does outperform, and I believe that's actually the way that the project in the initial paper where this structure was proposed, they used this class token method. But yeah, we can see here the accuracy starts lower for the mean method, but passes and winds up higher. Each of them with respectable values and very similar performance, but reaching approximately 57–58%. So just to remind you guys what we're doing here, we're taking those images in one of 10 classes, and we're getting it right 57 or 58% of the time. Similarly, equivalent results for the loss here. The mean is worse initially and learns to become better. Anyway, hopefully that was helpful for you guys. Hopefully I made it clear how some of the stuff in this process is analogous to the data flow from the machine learning part. Thanks for watching.